Okay, so let's get set up, and then we'll talk about where we are in the semester, assignments, all that stuff. I have quite a few examples I want to go through today, so I want to try to get started as soon as possible. That's why. There we go. Perfect. Okay, so while you're getting set up, here's where we're at. So assignment number 3. Can't remember if I graded that. Did I grade that for this class?
I don't think so.
Okay, I'll make sure to get that graded then. That one should be quick to grade. And then assignment number 4. I'm putting this on kind of a due date that is not lining up with class, so keep track of that.
You said assignment number 3?
For number 4.
3 is graded.
Yeah.
Oh, 3 is graded?
Yeah.
Okay. Assignment number 4, notice that it's due on a Friday. The reason I did that is in case I didn't want to make it a full 2 weeks because that's going out a little bit too far, but a week and a couple extra days. So if we talk about any difficulties you're having next week, it'll give you another couple days to get that turned in. So just keep track of the date. We'll talk about this in a minute. It's not that difficult. Essentially, it's just taking some algorithm that we've done in class before, finding the average of a number, and I want you to turn that into a function. So it should be fairly straightforward. One of the things I was thinking about doing is tomorrow, I'll send out an announcement later today. So over the when COVID first closed down the school back in, I guess that would have been March, I wrote some software for doing remote tutoring, and it's a little bit different than Blackboard's built-in software. It's basically like you get put in a queue, almost like if you call tech support, you get put in a queue. And we have a couple of tutors, and I'm thinking about, we did a little bit over the summer, but not that many people used it because not that many people take summer classes. But I'm thinking about using that because I'm noticing between this class and a couple other classes, some people are having some difficulty. So what I'm thinking about doing is tomorrow, doing some time. You may get me, you may get one of the tutors, but it just kind of puts you in a queue. It's very simple. I try to make it as simple as possible. You just go to a website, you click Get Help. There's a drop down for the class, and then you just kind of wait in a queue until somebody who's qualified for that class. So I'm going to send out an announcement if you need additional help for this class, or if you have another class with me. But I'll send out some information about that because I did notice on a couple of the assignment number 3s some difficulties, and I want to get those difficulties solved before we move on to more difficult stuff because it's gonna ramp up very quickly. A lot of this stuff is just stuff from COP2030, just learning how to do it in a different programming language. But after assignment number 4, we're going to start to do stuff that's completely different that probably has nothing to do with anything you did in COP2030. So just keep an eye out for that. I'll send out an announcement for that for anybody who needs additional help. Okay, so let's get right into it. So I'll explain assignment number 4 in a little bit. Let's just get right to. Oh, by the way, don't forget you have this website here too. This seems to be a halfway decent. It's not really necessarily complete, but it's simple, and I think that's better for most people. Is just to have information you can actually understand than have it complete and have it overly technically detailed. That's one of the complaints I have with the C++ book, is that it's very complete, but very few students actually read it because it's just overly detailed. Just out of curiosity, how many people found that to be the case? It was kind of a difficult to read book, yeah.
It's full of techno babble that at the time I had no idea what meant.
Yeah. That's why I like some of these websites, is that they might not be as technically complete, but the information they do give you is pretty easy to understand, like conditionals. you know, to me this is a lot easier to digest than 30 pages of stuff. So, but don't forget, so you have that available. I'm going to offer some additional tutoring help. Now, what I'm probably going to do, just to let you know ahead of time, I'm probably going to limit the sessions to about 10 minutes. That way, you know, I'm only one person in case anybody else is waiting, that they can get some additional help too. So, okay.
Found out the website Geeks for Geeks. It's all one word. Helps a lot.
Okay, yeah, send me the link and I can add that here when you think about it. Okay, let's get right into our first example. We've already done this, but because this is such an important example and it goes into your assignment, that I want to make sure that you're good on this. So remember how lists work. Lists are collections of things. They could be numbers, they can be strings, they can be other data types that we haven't even talked about yet. Let's do an example where we've got, and we've gone through this finding the average of a number a bunch of times. It's that I could have a bunch of individual variables, but that's not super useful because I can't loop over that. I have to hard code some sort of equation that works with a very small number. Like I could have like 5 variables, but imagine 5 million variables. That's not really practical anymore. So what I have to do is put that inside some sort of what's called a collection. You've probably seen collections from COP2030 with arrays, but lists are very similar. They're similar enough that I don't really need to get into the differences too much. And so let's say, for example, we've got some list called numbers. Doesn't really matter what these numbers are. Don't forget, you can do this. Oops, let's not use exact numbers. So we've got 1, 2, 3, 4, 5 numbers. Is this large enough that everyone can, I can go a little larger. That should be good. And remember that I can access these individually. So I could say numbers, remember they're indexed from 0. So if I did number 0, it would print 1.2, but I have to actually use print, so let's do that. And then if I wanted to go 0, 1, 2, 3, print the last element, so it'd be 0, 1, 2, 3, 4 would actually print the 5th element, because we start counting from 0, we get 9.1. But very often, we don't really care about accessing things like this. What we usually like to do, I'll just put a comment so you know that you can do this. So what I could do, don't type this because I'm just going to comment it out. Just let you know. What we could do, kind of the C or C++ or JavaScript way, would be like for I in, this gives me 5 numbers, and then I could do like this. And that would print each number. But we actually have a nicer way. What we can do is we can directly get each number. So we can say for number in numbers, and it goes through each number one at a time. Print number. Okay, so this is the version I want you to have for your notes. So don't worry about this, but do have this typed out. It does the same thing. To me, this is a simpler syntax. In general, we actually don't care about the offset that often. The times we do care, we have a special function called enumerate, which we can use as well, but most of the time I find myself just using this syntax. Most of the time when I use enumerate, and I actually do need that I, it's just because I have like 10 million records to process, and what I'll do is I'll just put a little print statement in there that every 10,000th record I'll print I or something like that. But for the most part, this is good enough. And so what this does is it goes through each element of the list and it assigns it to number, so that way inside of the for loop, we have access to each number. Now, to find the average, what do we have to do? We have to take all the numbers, add them up, and then divide by the length of it. So let's do the first part, which is we'll create a variable called total. And initially, the total is going to be 0, because we have to give it an initial value. You'll see why here in a second. I'll just comment this out. And then each time through, we'll say that, okay, the new total, this is called an accumulator, by the way. I can reassign values. I don't have to, one of the difficult things I see people struggle with in COP2030 is they think that variables are like a one-time thing. You can reuse variables. You can reassign values over and over and over, and I can actually accumulate values and kind of, I mean, that's just the term. I can accumulate values in there. And so what I can do each time through is I can say that, okay, the new total is going to be the old total plus whatever number. So the first time through, it'll be 0. Total will be 0. It'll be 0 plus 1.2. And the next time through, total is 1.2. So it'll be 1.2 plus 5.3, which is going to be 6.5. So it'll be 6.5 minus, or it'll be plus minus 1.4. And you get the idea. It'll keep on doing that. So that's why we have to initialize it to 0. And that's just some simple, if you remember from algebra, 0 plus a number is just going to be that number. So that's why we use 0 as a starting point. Now, just so you know, this is such a common task where we take some value. By the way, so it actually evaluates on the right-hand side first. Let's make sure everyone understands that. This is true of most languages. What we actually do is that we look at the right-hand side first, get some answer. In this case, it's going to be total plus number. Then it stores it over here. Normally, we read our code left to right, but in this case, it's actually, we evaluate this, get some answer, and then store it over here. This is such a common thing that we actually have a shortcut for this, that we can say total is plus equals number. And actually just, these two are equivalent, but you'll much more frequently see this version of it. Yeah, it's interesting because a lot of these languages don't want to reinvent the wheel. So things that work, they just copy over from another language. So this plus equals probably, I would say every language I've ever programmed in has it, except for maybe assembly. But this is a very, very common operator. Remember how these code blocks work is that we use indentation. So we have the colon here, and then we've indented one level. So this means that this is all part of the for loop. But once we go back in the other direction, outdent it, I guess, I got to look that up. I don't know what the correct term is. This means that because I'm no longer indented, we get a little visual cue here from the editor. We get this line. This didn't print 5 times. This just printed the once. Okay. So at this point, we should have the total. So I should be able to print total. Now, what do we do with that total? Is that right? Did I just happen to do some numbers that added up? So, 5. Yeah, okay. Now, the goal of the program wasn't to get the total, it was to get the average. So, average is equal to, well, we could say that it's the total, the summation, divided by 5. So we could do that. But what happens if I add another number? I have to change it in 2 spots. We generally don't want to do that. So there's a function called len for length that we can actually get the length of this. So len, pass it my numbers list. This version is much more resilient to change because Code is a living thing. It's very rare that you write a program and then it stays static. It stays like that forever. Usually what happens is you write some code. It generally works. Somebody finds a bug or wants a feature a few months later, and you have to go back to that code and modify it. So you want to avoid changing things and hard coding things and having to do things in multiple spots. In this case, this is very good because no matter how large this list gets, it's just going to automatically calculate and return the correct value. Same thing here, because we've done this with a for loop and we haven't hard coded any numbers. Whether this is 5 or 5 million numbers, it's still going to work the same. It's just going to loop over each individual number. Okay, any questions about this?
Isn't this our homework?
What's that?
Isn't this our homework?
So what I do is yes, it's part of it. So what I do for the homework is next we're going to talk about functions, and then so I say take this that we've created here and turn this into a function. Make it a reusable thing so you don't have to, every time you wanted to find the average, you'd have to write this. You could just make a function called average and then just pass it a list. Okay, so that's the last we'll talk about right this second on lists. Let's talk about functions. Now, the idea of a function is that it's reusable code. Many times other people write the function for you, sometimes you write it yourself, but either way, the idea is that somebody's supposed to call the function and you've got very clear defined inputs, things that you send to the function, and then you get an output out of it. So let's do a very trivial function. I think we've already done this example, but I like it because it just kind of, and before we used A and B, but just to let you know, it doesn't have to always be A and B. We'll do this. We'll say num1, num2. So this is a function that we're defining. We use this special keyword def. This is the name of the function, and these are the two variables that we're taking in. And we'll say that result is equal to num1 plus num2. And then we use this keyword return. Notice that turns blue, so we know that it's something special. Return result. So I always like to think of the analogy of a box, is that on one side of the box, we give the function some inputs. In this case, it's going to be 2 numbers. On the other side of the box, it's going to give us some result. We don't really care what happens on the inside. All we care about is that we have clearly defined things that we give to our function, and then we get a clearly known ahead of time basically what it's going to give to us. Now, what's a little bit different than other languages, because we don't have to define the types in Python. Notice that we don't have, in other languages, you might have like return void or return int or return double. We don't have that. So it's sort of up to us to keep track of that, or maybe as a comment inside of our function to say the type of data it's going to return. This can be very frustrating when you're dealing with functions because you don't really know what it's expecting and necessarily what it's going to return. But usually, kind of the Python way to do things is that you just you put it as a comment so somebody later can look at the comment and know exactly how your function works, which is not great, but it's practical for a language that doesn't really make you do typing ahead of time. So this is the name of the function that we're calling it. These are the inputs. Now I will tell you one advantage of this. In other languages, you might have an integer num1, and so 2 ints and 2 doubles. In other languages, you would have to make 2 different versions of the function. But because this doesn't really care whether it's an int or a double, it just has to be 2 data types that support the plus, the addition operation. You can actually use this on ints, floats. You could even technically use this on strings. Anything that supports the plus operator. So there are some advantages to not having to define types ahead of time. They actually call this duck typing. It's kind of a funny name. You don't specify the type ahead of time. It's like that old saying, if it quacks like a duck, it's a duck, or something like that. But the basic idea is that I don't really care what data type it is. It just has to support the plus operation. So I don't care if it's a float or an int, because they both support plus. So you get the idea. So that's how I define a function. How do I actually use it? So the way I use it is that I call the function add to numbers, and I pass it two numbers. So here, these are the variables. So I've passed it 3 and 4. Now when the function actually gets called, it's going to have num1 is going to be 3, num2 is going to be 4, 3 plus 4. It's going to store it here. Now make sure you understand how this keyword return, because this is, remember I told you that outside of the other end of the box, we've got inputs and then we've got outputs on the other side. This is the special keyword that returns it. So we do 3, 4. It's going to do 3 plus 4, which is 7, and it's going to return 7, and it's going to know that's the return value. But we've run this, and we just kind of let the return value just kind of go away. We didn't really do anything with it. So we want to store that somewhere. So what we do is we can say total is equal to, and because this returns that value, it'll be stored in total, and then we can say print total. So when we call this function, when it returns the result, it returns it from wherever we call it, and we can store it over here. We can use the equal sign, and then we just can print it out just to show that it works. Okay, so that's the basic structure of a function. Any questions? Let's do a slightly more complex function. So your assignment, I give you a list. So create a program which finds the average of this list. The program has to use a function called average. So you're going to create a function called average. What's nice is I already gave you the algorithm to find the average of a list. That's the first example here. But you can't just imagine a program where you needed this code 50 different times. Are you just going to copy and paste this code in 50 different spots? No, that'd be terrible, because if there's ever a bug, if you ever want to add something different to it, you're going to have to change it in 50 different spots. You might introduce new bugs. You might forget to change it in different spots. It's very time consuming. That's why we have functions. So I gave you some algorithm here, and the idea is that you're going to turn it into a reusable function called average. Let's go through that process, but let's go through it for something simpler. If I've got a list of values, I might want to find the largest value. Okay, so let's do that. So I've got some list, and I'll just be very generic. I'll just call it numbers is good. And again, some numbers. We can actually just to save time, let's just steal our list from before. And let's change this last value to 1.1. So this program is going to find the largest value. So at the very least, we know we're going to have to loop through something. So let's write our loop for number in numbers. Let's just print number, just so we know that we're actually getting. Okay, so we're getting all those values. So a very simple algorithm that we can use is say, okay, if as I go through this, let's say I'm going to assume 1.2 is the largest value. Okay, I look at the next number. Okay, is 5.3 larger than 1.2? Yes. Okay, so that's the new largest value. Is minus 1.4 larger? No. Is minus 4.2 larger? No. Is 1.1 larger than 5.3? No. So after we look through all the numbers, this is still the largest number, so this is our largest number. So let's do this. So what we can say is assume that the first number is the largest number. There's a bunch of different ways to tackle this. I like this one the best because it tends to be the simplest that people can understand. And what's the first number? Square bracket 0. So remember, we start counting from 0. So 0, 1, 2, 3, 4. So assume that number's 0, which is 1.2. Assume that's going to be the largest value. Then as we go through our numbers, we can say, if the number I'm currently looking at is greater than the previous largest number, the new largest number is the number that I just saw. So again, that's just a formal description of what we just did informally, is that we said, okay, is 5.3 larger than 1.2? Yes. Well, that's the new largest number. Is negative 1.4? No. So we just don't do anything. What about this? No. We don't do anything. Here we don't do anything. So then finally, when we finish our loop, we know that that's the largest. Now, a lot of times we have to be formal, pretty much all the time in programming. We have to be formal about how we do things. There's a little bit of a thing that I kind of waved my hands and didn't really mention. What happens the first time through? What are we comparing? The first time through, we're actually comparing 1.2 with 1.2. Because I assume that the largest number is this, and then it starts from the beginning. So it says, if 1.2 is larger than 1.2, but it turns out it doesn't matter. It's just like a throwaway value because all we're doing is wasting one cycle. It's not that, but yeah, exactly. It's if we are comparing a million values, then it's at some point it's just like it doesn't really matter too much. There's another method. I don't really like it. It's basically set it to the smallest possible value because computers are finite. So there is actually the most negative value possible. To me, it's a little bit less clear for most people. So that's the way I used to do it, and then people would get like a little bit confused. So I switched over to this method. To me, this makes more sense for most people. Just start off with the first number, assume that it's the largest number, and then from there, keep on comparing it against the next number. Pretty straightforward algorithm. Does anybody have any questions on this? So let's take it to the next step. Let's turn this into a function. That way, if I've got a list of numbers, all I have to do is call this function. Okay, so generally we like to put our functions at the top. So let's just give ourselves some room here. And we're going to call this function maxVal for maximum value. Put our colon. And what we're going to do is we're going to take in a list called numbers. So we're going to take in numbers. Remember, we have to have a very clear defined input. If I'm finding the maximum value, you can imagine a box. What is that box expecting? It's expecting a list of numbers. right? So if I have a bunch of numbers and I want to find the maximum value, I have to give the box a list of numbers, and then what is it going to return on the other side? What is it going to output? Exactly, the highest value. So we have to always have that in mind. For making good functions, one of the problems I've noticed is that sometimes people take functions and they just kind of use it to chop their program up into smaller pieces. That's not really it. You have to kind of think about it in the kind of the mathematical sense, is that we've got a very clear defined input and a very clear defined output. So I'm taking in all these numbers. I'm just going to put a comment right here because we're going to use these numbers later. Actually, we'll just get rid of it. We'll make up some new numbers. And then here's my algorithm. So what I can do is I can take this algorithm, I can paste it up here, and then remember that we can just take this, highlight it, hit the tab key, and now this is a part of that function. And let's say I've got a bunch of grades and I just want to find my highest grade. So let's make a list called grades. So let's say on the first test I got a 90.2. Next one I got and then I call max val on these grades. Be aware of where the indentations are. So actually that's let's do this. I generally don't like to make it the last value to test. So let's do this. Let's change this to we'll just change this to a 98 and we'll just change this to an 88. It's generally, when you're testing algorithms like this, you generally don't want, you want it to be a middle value. You don't want it to be the first or last, because if there's an error with your algorithm, it can be kind of tough to spot. So in this case, I changed these around, and 98.4 should be when it eventually runs, the highest. So our algorithm still works. However, there's a problem, and it's not super obvious because it looks like it ran. And it's not really a logic problem. It's not a syntax error. Does anybody see, if we go back to our definition of we take in inputs and then we have a very clearly defined output, does anybody see any problem with the way we've designed this max val function?
You can't take any values in for grade.
What's that?
You can't take any values in for grade, like you can't
Oh, I see what you're saying. No, don't worry about that too much so far. Our definition is that
no return.
No return. It's a very subtle thing that a lot of new programmers don't see right away, but you want to you really, really want to create your functions and think back to that definition. What things am I taking in and what things am I returning? I don't want to print the largest value. So let's take a step back here. Okay, imagine if we're writing code that's not just on a regular computer. Let's say, for example, we're very advanced. We're writing your code for our car's fuel injection system, or writing code for a jet airliner or something like that. It's not going to have a keyboard and mouse. So this print function is essentially useless, right? If I'm in your car's fuel injection system. So what that means is that this version of the function would either be useless or have to be modified. We want to write our functions in a way that they're completely reusable. Depending on what's called I/O, generally makes a function, it works, but it's not very resilient to change. I want a version of this function that is only dependent on a list of numbers. It doesn't matter if it's running on a video game console, if it's running on a PC, or if it's running in a car's, airbag system. So we want to avoid print statements, input and output, all that stuff inside of a function, because it really violates the definition of our function. What we want instead is that we want to return the largest value. And now, to me, this is very clear. This satisfies our definition, is that we've taken a list of numbers, and then on the output of the other side is that we give back the largest number. Let's go through a little bit more of an example here. Okay, so computers back in the 60s, when they first started using them, say, for banks, what did they look like? Did they have a keyboard and mouse? No, it was just like one of those green screens. Maybe it was like an 80-character wide terminal. But a lot of people wrote a lot of banking software back in the 60s and 70s. Has banking algorithms and accounting practices, have they really changed that much since the 60s? Not really, right? If I deposit money into the bank, they increase my value. I don't care about the details of whether it goes over the internet now or if it goes, over Wi-Fi. It doesn't really matter too much about the details. Basic accounting algorithms haven't essentially changed. So that software is probably still valid today. Okay, well, let's think 60s, 70s. What started to happen in the 80s? Computers started to get connected to networks. We had keyboards and mice. Rather than that green screen, somebody might want a nicer user interface. Okay. All those algorithms, if I had just assumed that those algorithms were going to only work on a green screen terminal, and now I've got to depend on a keyboard and mouse, that's going to cause some problems because I have to go back and rewrite the entire software system. Okay, let's say I rewrite that, and then what did we get in the 90s? We started to get websites. We started to get online banking. Okay, they rewrite the whole system to work with online banking because we're no longer getting the input from a keyboard and mouse. We're getting the input from a website. Okay, they rewrote the entire system. And then what happened in the early 2000s, mid-2000s, like 2008? What do we get? Smartphones. And then so they have to rewrite the whole thing again for smartphones. If you're smart about it and you write your algorithms and your code using functions, the only thing that you would have had to rewrite in that 50-year period is just the user interface. You could have used the exact same functions. So does that sort of make sense now why I'm kind of making a whole speech out of this? Is because it's very important that you write your software in that, is that the functions should be reusable no matter what the decade, no matter what the system, is that you've got very clear inputs and outputs. And a lot of times I think people think that a function is just a way to chop up your program into smaller bits. It's not really like that. You really, when you write a function, you want to be able to reuse it as many times in as many different places as possible. Okay. So with that, all that said, on your assignment, I don't want to see any inputs or outputs inside of the function. That violates one of the rules. If you want to get input, you have to do it outside the function or in a dedicated function. That's the one time it's okay, is if you have a dedicated function that its only purpose is to get input from the user or only purpose is to output something, then it's generally okay because you know ahead of time this is going to be a throwaway function one of these days. I'm not going to be able to reuse it. But it's usually pretty obvious stuff that you can reuse. In this case, max val, a list of numbers in the 60s and a list of numbers today, it's still a list of numbers. It doesn't matter if it's on a green screen terminal or on an app on your phone. Okay.
I remember in COP2030, you said that one of your former workplaces, like 70% of the code is like 40 years old.
Oh, yeah, exactly. That's actually a good story. Yeah, one of the places I worked, we worked in writing power system software, and some of the code, because they wrote it in such a good way that it was very clearly defined functions, and there was a lot with motors and all that sort of generators and all that stuff, the math on that's not changing. So they wrote a bunch of mathematical functions that they still use to this day because they wrote it in a way that it was reusable. Had they not done that, they would have every 20 years would have had to. So when they wrote that system, it was in a green screen terminal type thing. When I left, it was a Java-based graphical user interface, and they were able to keep that code throughout the years. So pretty interesting. Okay, so we took that basic algorithm, we had our clear definition, and I did that for max val. So we're almost there. I get the maximum. I called the function, but it just kind of drops the result. What do we have to do? We have to store that somewhere. So I'm going to say result is equal to, and then I'm going to print the result. Yeah, we could have called it whatever.
Oh,
If we wanted to, we could have called it. I don't want to use the term max. What's another highest maybe? So for your assignment, what you essentially have to do is take this first algorithm that we came for finding the average of a number, and then go through that process that we just went through. So rather than finding the maximum value, now you're just going to find the average. And it's not really grade average, it's just average. Well, anyway, you get the idea. Don't forget, don't hard code any sizes. Make sure you actually use the length function. So should be pretty straightforward. Just go through this process that we went through just here to turn this into, from our algorithm to a function. Go through that same process for this first example. Is everyone clear on that? Okay. So again, we're going to do some more examples today, but I don't want you to get confused. The examples that we do from here on out have nothing to do with your assignment. So don't try to start using techniques that we're going to use now thinking that it has nothing to do with the assignment. Everything that you need for assignment number 4 is in examples 1, 2, and 3. So let's open up another REPL. So let's do this. Let's talk about reading data from a file. How many people have heard of a file type called a CSV before? Comma separated values. It's very common, like with Excel files and stuff like that. Essentially, all it is just it's a plain text file. I want Notepad. It's a plain text file, and all you do is each line. Imagine Excel. Each line would represent a row, and each comma separation would represent. So, for example, if I've got Alice and her GPA is a 3.8 and she is a senior. Imagine splitting this at the commas, and then you could put this into each cell in Excel, and then on the next row we would have Bob 3.5 and Bob is a junior. So this type of file is called a CSV file, and we just have a bunch of comma separated values. Because it's such a simple file type and it's very convenient to work with, think about all the different things you could work with this. Imagine if somebody gave you all the sales transactions for a day. You might have one of the columns is the location, like which store it's at, which cashier was present during the transaction, the total price, the tax collected, maybe the number of items in that transaction, maybe a receipt number. So these CSV files are really, really nice because it's a plain text format, meaning that I can just open it up in Notepad and read it. There's a lot of formats that aren't like that. They're what's called binary. I can't just open it up and easily read it. But then it's also convenient to pass around the data because it's very easy to write code to read this. So let's do this. Let's take this and inside of REPL, and I'll give you a chance to type it out. What we can actually do is over here, notice that there's this files button. Make sure that we can actually see the files. And then we'll click add file. And notice that normally we just had the main.py. Let's make a file called data.csv, short for comma separated values. Again, so if you're not seeing this, just make sure this little files button, and then you went to add file, call it data.csv, and then go ahead and just type out what I typed. So we've got this simple data file. And by the way, make sure, because I want to do something, make sure that you've got the spaces in between, because I want to do something with this example. So make sure you have it typed out with these spaces in between. Is everyone good? So let's go back to our empty main.py file. If I want to read a file one by one, what I do is, we'll talk about this later. Just for right now, just recognize the code. I type with, and there's a function called open. And then we're going to open this data.csv file. So we're going to say data.csv as a very common name. This is just going to be our file handle. I just always like to use F. It's like a throwaway variable. What this line of code does is it gives us, through this variable F, it gives us access to this data.csv file. It lets us read from it. It's kind of a funny syntax. I don't really want to explain it too much now. It's just one of those things that you can just temporarily memorize. Really, the part you're actually doing is you're calling this function called open. And open returns a file handle, and that's this special keyword with. All this does is makes it so that later on, so we don't leave the file handle open, it automatically closes it for us. Now, this file handle F, it's kind of cool because we can actually read from it one line at a time. So let's do this. For line in F, just think of F. Remember how before we had a list? Imagine each line in the file is an element of the list. So this would be the 0th element, this whole row right here. This would be the first element. This would be the second element. And so we're reading it line by line from this file handle F. And then let's just do print line. Let's see what it actually gives us. What do you notice about those 3 lines? Do you see anything kind of a little bit strange from our original file? So look at this, and then look at our original file. Yeah, we have an extra new line. So we have these things called invisible characters. We actually don't see it, but every time we hit the enter key here, we actually got this invisible character right here, this / new line. It's invisible, we don't see it. But we need to get rid of that. We don't actually care about that extra new line. We don't care about that extra invisible character. We want to essentially chop it off, get rid of it. So there's this special function, and what it does is it strips out what's called white space, any extra spaces, tabs, or new lines. And so what we can do is we can say, okay, print line dot. We actually don't need it. Strip does both sides. We just need a version called rstrip because we just care about the right side. But we don't have to do that every single time. So what we can do, and this is just a pattern I use constantly. What I do is I say, okay, remember that we can reassign variables. I just say, okay, I don't really care about that extra new line. Just give me the version with the new line removed from the end. So it looks at this. It gives us the version of the string without the new line, and then it stores it back over here. So now we can just do print line. So we've got each line, but it's very common that we want to do processing on each, I guess we would call it the column, or it's really each cell. And so we don't care about having the whole line. What I want to be able to do is just access each one of these separated by the comma. Let's say, for example, I just wanted to print all the student names. So there's this function called split. So I'll do line dot split, and then we have to say where I want to split it, and I'm saying split it at every comma. Now, what do you notice about this? What data type is this with the square brackets? What's that thing called that we've actually been interacting with most of class today? Square brackets means that it's a list. So we actually have the split version. I've got a list of 3 things. It's going to be the name, the GPA, and their year. Okay, so rather than printing that, let's go ahead and store that somewhere. And so I can maybe make a variable called parts, which is a list of the different parts. And then if I just wanted to print the name, this is going to be parts 0. Because remember, each one of these is a list. It's a list of lists, essentially. I could say, okay, print parts 0. But we sort of want to avoid this because it's not super clear what parts 0 is. We always want to be clear. So one of the things we can actually do with this is rather than saying parts equals, we can do something called multiple assignment. So I'm going to comment these 2 lines out just because I don't like deleting code. During class, I like to just show you alternative ways. So rather than saying parts equals, really I've got their name, GPA, and I guess we could call that their year. And so what I can do with multiple assignment is I can say name, GPA, year is equal to line dot split. And then now rather than this awkward parts 0, I can just say print name. Or print their GPA. Let's do this. I was going to do something else with this example. I don't want it to get overly complicated. Let's just go back to our data.csv. Let's get rid of these spaces. What I was going to do is show you how to remove spaces from within, but maybe I'll do that next class. So we'll just have them all pushed together like this. So now if we run it, and then maybe one final thing. What data type do you think this should be?
Double.
Yeah, either a double or a float. Which so essentially some sort of decimal number. But right now, if I were to do type for GPA, what is it going to return? Yeah, it's going to be a string because it doesn't know. It assumes everything's a string. So one final thing that we could probably do is say, okay, well, I want GPA to actually be a float, and then now if I needed to do some sort of comparisons to see if like one GPA is larger than another person's GPA, I could do that. Just comment this out, and then let's just have one final F string. We haven't used these in a while. And so we'll say like name is name. Let's see how many we can fit on here. GPA is GPA. Year is year. By the way, this is a very, very common thing. Now, there are separate libraries for reading CSVs, but to be perfectly honest, if it's just a simple CSV that doesn't have to have special processing, I'll very often just write my own quick version like this where I just split it at the commas. It can get complicated because what if somebody uses escape characters? There are some complexities that we don't want to have to write our own, but if it's just a very simple version where you know that it's just going to be split at the comma, it's very common that I'll just do this rather than bringing in a whole separate CSV processing library. Now, we do have to be somewhat careful because we knew ahead of time that there were going to be three things: the name, the GPA, and the year. But say, for example, I was also expecting their phone number. It's going to throw an exception. It's saying that I was expecting to unpack 4 values, but I only got 3. So you do have to be kind of careful about this. It's sort of up to you as the programmer to know how many values you're supposed to be getting. Okay. Any questions on this? Okay, so this is essentially how you open a file, and a very common thing for us to do is just to read it one line at a time. We want to usually get rid of that extra new line at the end, and so this is what I do there. And then in the case of this, that we're reading a CSV, what we can use is this special function called split, and it'll split it out into a list, and it'll break it up based on this character. In this case, it's a comma. Now, we could have just used this list called parts, but we already know ahead of time how many columns it's going to be and have a pretty decent idea of the name. So what we can do is just do multiple assignments and say, okay, the name, GPA, and year, because on this side we know it's going to return 3 values, and it'll correctly place those values into each of those variables. So a couple more examples. So I think we started to talk about dictionaries, correct? Okay. So let's do a quick review of dictionaries. So the idea of a dictionary is it's sort of like a list, but rather than having to deal with a number for the offset, we come up with what we call a key. Most of the time the key is a string. So let's do this. Let's say, for example, we have students equals, and then before, if we wanted to create an empty list, we would do the square brackets, but for a dictionary, we use the curly braces. And we could just confirm that if we did print type students, it should show up as a dictionary. Perfect. And let's pretend that our dictionary, the way it's set up, is that the key is the student's name. So we could say students Alice. So that's going to be the key, right? Rather than having like 0, 1, 2, it's going to be their name. And let's say, for example, I wanted to point to Alice's GPA. We'll do the same thing with Alice, Bob, and Charlie. I don't remember exactly what I made the GPAs before, but we'll just make something up. So this is how we do assignment. Now if I wanted to retrieve a value, all I'd have to do is print students Bob, and I'd get Bob's value. Might seem kind of silly so far because, well, I could have just created 3 variables called Alice, Bob, and Charles. One thing is that we can, because it's a collection, we can actually run a for loop over it. So there's that. but I don't want to talk about that just yet. I just wanted, so this is the basic syntax, is that we create an empty dictionary with the curly braces. We can define it ahead of time, which I might show you maybe next class, but maybe if we have time this class. But right now, let's just say we have an empty dictionary, and I've added 3 students, and this is each student's GPA. To access the values, we would just do this. So, looking at this previous example, it actually turns out it may be more natural, rather than keeping it line by line in a list, it actually might be more natural to keep it as a dictionary. So let's do this. Maybe I guess we'll just start a new example for this. Rather than hard coding the GPAs like this, because what happens if I get a new student? What do I have to do? I have to modify the program. In general, we don't want to do that. We don't want to modify the program. Anytime we're modifying the program, we can introduce bugs. We may not be authorized to modify the code. It may be a closed source program where we don't even have necessarily access to the code. So what we tend to do instead is we tend to put data inside of separate files. That way we can split our code and our data. So it's very rare that we would ever hard code a bunch of students in here like this. What we tend to actually do is read it from a file. So let's combine this, and let's make a student dictionary that we read from the file. That'll be, I think, the last example that we get through today. So let's open up a new REPL, and then we can be lazy a little bit here, and we'll copy our data.csv. So we'll go to add file, we'll call it data.csv, and we'll paste in Alice, Bob, and Charles. So again, remember you've got this, so this is a new REPL. Make sure this file shows that you can add file. We call that new file data.csv. We paste it in. If you already closed the tab, you can type this in really quick. By the way, be careful. Don't put an extra new line at the end. Notice that it only says 3 lines. Even though visually this doesn't look much different, it actually is. I'll explain maybe another time. Just make sure that it's only 3 lines, that you don't see a 4th line. And let's go through that basic pattern that we did. Everyone has this data.csv set up. Let's go through that basic pattern again. So it was with open in quotes data.csv as f for line in f line, get rid of that extra new line at the end. Then we're going to say name, GPA, year is going to be, we're going to split at the commas. And just to make sure that we're reading it correctly, let's just print here, I guess. So now what we can do is we can start to build out a dictionary. So let's do this. At the top of our file, let's say, just like we did over here, we'll say students equals, so we'll make basically what a data structure. Students is equal to, and then empty dictionary. And then now what we can do is say, okay, students name is equal to GPA. If you want to make it a float, you can. We're not going to do anything that needs to be a float, so this is sufficient. And then after we've processed that file and stored it inside of a dictionary, notice that we haven't hard-coded anybody's information at all. And then if later on I wanted to print Bob's information, I can, because I've read it from the file and Bob happens to be in the file. Now again, you actually typically wouldn't hard-code Bob in here like this. You would maybe make it interactive and say, okay, which student are you looking for? Something like that. But for now, this is okay. Now we can actually take this a step further, because notice that we're throwing away the year. And it shouldn't be a surprise that for most students, you probably want to track many things about them, not just their GPA. What we can actually do is, rather than hard coding a GPA like this, we can actually make a dictionary of dictionaries, which is very, very common. So what I can do here is, rather than pointing it to a GPA, I can say it's the dictionary, and then, so we can set it to an empty dictionary. We can actually define a dictionary at the time of creating it. So what I mean is I can say that the GPA is equal to, so don't change your example, because I'm going to flip immediately back over just for time purposes. And so what we can actually do is say that Alice points to a dictionary containing GPA, which is 3.8, and then the year, which is senior. We'll go over this in more detail as our first example next class. This is just to kind of give you a preview of where we're going. And so what we can actually do is, rather than just, like I said, hard coding that as a GPA, we can go back over here, and rather than saying that student name is equal to GPA, we can say that it's equal to the dictionary GPA, which points to this GPA, and the key year, which points to the variable year. And now, oops, sorry, it's a colon. Now if I go to print Bob, I don't just get back the GPA, I get back a dictionary containing the GPA and the year. And it's a little bit tough to see. I just want to, let's do this. We don't really need this anymore. There we go. And then now if I wanted to get Bob's individual GPA, I would, because it's a dictionary of dictionaries, I would say Bob GPA. We're probably going to spend at least a couple weeks with these data structures, because this is really what makes these languages like Python very powerful. Same thing with JavaScript, is that you can create very interesting data structures, and you can take these data structures, serialize them into different formats like JSON, and then pass them to other programs over the network, or store them on the disk for later. But this is kind of a preview. It's okay if you didn't fully understand this example. I know how to kind of go through it a little bit fast, but next class we'll start with dictionaries. And don't get confused. All this dictionary stuff has nothing to do with this assignment. Again, for that assignment, it's just examples 1, 2, and 3. Okay. So watch out for an announcement. So any questions on this particular example? Okay. So watch out for an announcement. Like I said, I'm going to see what I can do to arrange some sort of tutoring. And again, it'll probably have to be for very short periods, just so everyone gets a chance to get their questions answered. So I'll send out an announcement about that. We didn't drop any frames. Perfect. So no assignments on dictionaries right now. Just make sure that you concentrate on this assignment about functions and basic algorithms and turning algorithms into functions, okay? Remember the due date. It's not due on a Wednesday like normal. I give you an extra couple days just to be able to work on it. And I think that's it. So any questions on anything? Everyone's good. Okay, if you think of anything, go ahead and send me an email, and then look out for an announcement, and I'll give some more details on that. Otherwise, stay safe, and I'll see